Okay, so welcome to the online student PD reading seminar. Let me introduce the speaker today, Doanh Pham, who just finished his PhD at Rutgers with Professor Yan Lee, and he's sort of on the process of sort of taking the next postdoc position at Beijing Normal University. Today, Doanh going to talk about some geometric inequalities by the ABP method. Please, Doanh.
Thank you for your invitation and very nice introduction. It is a great pleasure for me to speak here. So today I'm going to talk about the ABP method and applications in geometric inequalities. Briefly, what is the ABP method? Well, the method is motivated by the classical Alexandrov-Backelmann-Pucci maximum principle. So that's why we call it the ABP method. So let omega be a smooth bounded domain in the Euclidean space of dimension n, and U is a smooth function on omega. Then there is a notion called the upper contact set of U, which is defined as a set of points where the tangent hyperplane lies above the entire gravity. So formally, gamma U is given by this formula. So the ABP method is about analyzing the upper contact set of a function. So the ABP maximum principle says that the supremum over the entire omega of U is controlled by the supremum of U on a boundary plus diameter over the volume unit ball to the 1 over n multiplied by integral on gamma U, determinant of Hessian U to the 1 over n. So this ABP maximum principle is classical, and it is important in theory of PDEs. Like you can find this ABP maximum principle in the classical book of Gilbert and Schrödinger, for example. So the idea of this proof is again is analyzing the upper contact set. So for now, we assume that U is non-positive on the boundary of omega. So if we let x0 be a positive maximum point of U, right, then we have the following lemma. We have that the ball with the radius ux0 over diameter center at 0 is a subset of the total gradient of U in gamma U. Let's quickly look at the proof. It is a short proof, but it is important for later idea. So we fix a point inside the ball. We fix a ball. We fix a point inside the ball, and then we consider the Legendre transform of U. And so this is up to the side V defined by this formula is the Legendre transform of U. And we observe that if X is on the boundary, then if Vx is less than or equals to Ux plus the norm of psi multiplied with the norm of X minus X0. And because the way we choose a psi, the norm of psi is bounded by Ux0 over diameter. And X minus X0 is less than diameter. Therefore, V is going to be less than Ux plus Ux0. But at the beginning, we assume that U is non-positive on the boundary. And because of x is on the boundary, so ux is non-positive. And therefore, Vx is less than ux0. And by the formula of Vx, Vx0 is the same as ux0. So meaning the supremum of V on the boundary is less than Vx0. So V has an interior maximum point. Let's call it Y. At the interior maximum point, the gradient of V is 0. By direct computing, the gradient of V is given by the gradient of U minus psi. So this means the gradient of U at Y is psi. And moreover, by the definition of V, we can see that Y is in the upper contact set of U. So this finished the proof of the lemma. So it basically it says that this ball with the radius ux0 over diameter is the subset of a total gradient. So if we take the volume, then the volume of the ball must be less than or equals to the volume of the total gradient of U in gamma U. So we take the volume. So on the left-hand side, it is the volume of the ball. And here on the right-hand side is the volume of the total gradient of U in gamma U. And next, we apply the area formula. So the volume of the gradient of U in gamma U is less than the integral over gamma U, determinant of Hessian. And that finishes the proof of the ABP maximum principle. So the next demonstration of the ABP method in geometric inequalities is the Capret's idea of the proof of the isoparametric inequality. So essentially, the isoparametric inequality says that among all the solids with the same volume, the ball has the least surface area. So the idea of Capret proofs is based on analyzing the contact set, just like in the proof of the ABP maximum principle. So by scaling, we can assume that the surface area of omega is n times the volume. So so we make this so it looks like a ball, right? So because if you think like a ball, then the surface area is n times the volume. So we make this it is convenient for us later. Then trivially, this means integral in omega n equals to the integral on a boundary. It is trivial. Then by the theory of elliptic PTE, we have the solution to the Neumann boundary condition. Laplacian U equals to n inside, and normal gradient of U is 1 on the boundary. So we have a little bit remark here. So if there is a solution to the following system of equation, then if we integrate the function U over omega, integrate Laplacian U over omega, then we would have integral of over omega of n equals to integral omega of Laplacian U. And by the Green theorem, we can continue this chain of equalities by the integral over the boundary of normal derivative, which is 1. And this is exactly the scaling. So which means the scaling is the necessary condition for the existence of the solution U. And it turns out that this scaling is also the sufficient condition for the equations to have a solution. So because of the scaling that we made, we need to prove that the volume of the unit ball is less than the volume of omega. And we recall here that you solve the equations. Then we define the lower contact set of U, which is the points where the tangent hyperplane lies below the graph. So formally, it is given by this. It is just the points where the tangent hyperplane lies below the graph. Then, similar to the ABP maximum principle, we have some ball is contained in the gradient of the total gradient of U in gamma U. To see this, we fix a point inside the unit ball. Then similar to the ABP maximum principle, we consider the Legendre transform. Well, let X0 be a global minimum point of V. If X0 is on a boundary, then the normal derivative of V has to be negative, at least non-positive. So it is at least non-positive. Then by the equation of V, we can compute the normal derivative of V, which is the normal derivative of U minus the inner product between psi and the normal vector, the normal outer unit vector. By the equation of U, the normal derivative on the boundary is 1. So it's just 1 minus the inner product between psi and U. And because psi is in the unit ball and U is a unit vector, so 1 minus the inner product between them has to be positive. So we have a contradiction here. Therefore, the global minimum of V has to be inside omega. So as an interior minimum, the gradient of V at X0 is 0. And that means that psi is the same as the gradient of U at X0. And by the definition of the lower contact set, we see that X0 is in gamma U. So this finishes the proof of the lemma. So one important property of gamma U that we are going to exploit is the fact that the Hessian of U is non-negative on gamma U. Yeah. So we can apply the arithmetic geometric mean inequality to see that 1 is the average of the trace of the Hessian of U. This is by the definition of U. And then it is greater than or equals to the determinant of Hessian over to the 1 over n for all x in gamma U. So by the lemma, if we take the volume, because the lemma says that the unit ball is a subset of the total gradient of U in gamma U. So if we take the volume, we will have this relation. And now by the area formula, this is less than or equals to the integral over gamma u of determinant of Hessian. And determinant of Hessian is less than 1. We just show it above. Therefore, the volume of unit ball is less than or equals to the volume of omega. And that finishes the proof of the isoparametric inequalities. It is a very short and elegant proof by Capre. And we are going to explore this idea later. So we make some observations. So there are two properties of gamma u that we actually need. The first one is the fact that the unit ball is inside, is the subset of the total gradient of u in the lower contact set. And secondly, the Hessian of u is non-negative on the contact set. So the Capres proof to still work if we modify gamma u to be a smaller set, saying that it is a set of points where the gradient of u is less than 1 and the Hessian of u is non-negative. And if we replace this gamma set, gamma u by the we replace the lower contact set by this new gamma u, then the whole proof still works. So next, we are going to look at a generalization of the isoparametric inequality. It is a Sobolev type inequality for positive symmetric tensor. So let A be an n by n tensor, and by a tensor we mean a matrix value function in a bounded domain. Then the divergence of A is a vector field given by this formula. So the ith component of divergence of A is just the divergence of the ith row of A. So this is the meaning, the definition of divergence of a matrix. When the vector divergence A is 0, we say that A is divergence free. So there's a theorem says that if omega is a smooth bounded domain in Rn, and A is a smooth uniformly positive symmetric tensor on omega, then we have a Sobolev type inequality for A. It will take the following form. We will look at this. This is very similar to the Sobolev inequality, the usual Sobolev inequality, which we will look at it later. Well, about this. This theorem seems to have important applications in fluid dynamics, as pointed out by Dennis Sear in 2018 when he proved this theorem for convex domain and applied this inequality to study fluid dynamics. He used the optimal transport technique instead of the ABP method. And because the regularity issue, the convexity of omega is required in Dennis Sear's argument. So why we call this the Sobolev type inequality? Because if you take A to be F, to be a function multiple of the identity matrix, then you can recover the sharp constant for the Sobolev inequality. So we sketch of the proof, which has a very similar spirit with Cabre's idea. So after multiplying A by a positive constant, we can assume this relation. We make this, we choose a constant to make A to satisfy this 3.1 relation to have a solution to the 3.2 equations. Again, the existence of this solution is guaranteed by standard theory in elliptic PDE. Let's just like the remark in the proof by Cabre, if there's a solution to the equations, then you integrate over omega. Then when you integrate over omega, you will recover exactly the equation 3.1. So 3.1 is the necessary and sufficient condition for 3.2 to have a solution. Because of the scaling, then we need to show that the volume of the unit ball is at most I mean the integral over omega of determinant of A is greater than or equal to the volume of the unit ball. So like in the observation that we made after the proof of Cabre, if we define right by the remark after the proof by Cabre, we pointed out two properties of the contact set that we actually need. So here we define the contact set like that. So it is the point where the gradient of U is less than 1 and Hessian is non-negative. Then similar to Cabre's argument, we would have the unit ball is the same. So instead of a subset, now it is the same because we modify gamma U so that the gradient of Ux is less than 1. So because of that, one can easily see that the gradient of U in gamma U is a subset of the unit ball. So the right-hand side is the subset of the unit ball. And by looking at the Legendre transform, we can show the reverse relation, just like in the proof of Cabre. Moreover, we can show that the determinant of Hessian of U is less than or equals to determinant of A to the power 1 over n minus 1 on the modified lower contact set. And in the proof, we use the fact that the gradient of U is less than 1 on gamma U. And that's why we modify gamma U, right? And it turns out that this modified lower contact set is more convenient for our purposes. So if we put these things together, we take the volume, then the volume of unit ball is less than or equals to the volume of the total gradient of U in gamma U. And then next we apply the area formula so that the volume of the gradient of U in gamma U is less than the integral on gamma U of determinant of Hessian. And the next term is by lemma 2, the second lemma. All right. And that finishes the proof. Okay. So one can say that our proof is very inspired by Cabre's argument.
Doanh, can I have a question?
Yes, yes.
So in the PDE earlier, right? I mean, the divergent form elliptic equation, you actually don't really need that A is symmetric. So in which part that you use that is symmetric in your proof for this result?
Yeah, that is a great question. Yes. Later, when there's like a generalized like in AMGM inequality, like in in Cabra's proof, when we there's a part when we apply the arithmetic and geometric mean inequality, saying that the trace of A is greater than or equals to the determinant of A over N to 1 over N or something like that. Yeah. And there's a more generalized version saying that if A and B, if you have two matrices A and B, which are non-negative and symmetric, then the trace of A times B is greater than or equals to determinant of A times B over N to the 1 over N, something like that.
Thank you. Thank you.
Yeah. Okay. So next, we are going to look at logarithmic Sobolev inequality for minimal submanifold of the unit sphere. So log Sobolev inequalities are important in analysis and geometry. For example, the log Sobolev inequality for Gaussian space is essential in probability theory. So the classical log Sobolev inequality for the unit sphere says that, takes the following form. It says that for every smooth positive function on a unit sphere, you have the integral Sn of f log f plus log of the volume of Sn minus integral of f times log integral of f is controlled by the integral of gradient square f, integral of f square over f, which the equality holds if and only if f is a constant. So if we view Sn as the equator of the bigger unit sphere, then Sn is a totally geodesic minimal hypersurface of the bigger sphere. So the next theorem says that if sigma is any closed n-dimensional submanifold of Sn plus 1, then we have a similar inequality with some deficit constant on the right-hand side. So let's look at the classical log Sobolev for the unit sphere. On the left-hand side, it is log of Sn. On the right-hand side, it is 1 over 2n. In the next theorem, the constant on the left-hand side is still log n. However, the constant on the right-hand side is not as sharp. However, we still have the rigidity statement says that the equality holds if and only if f is constant, then and sigma is a totally geodesic n-sphere. Well, even though we don't have a sharp constant, the equality can happen because in that case, both the left and the right-hand side are 0. We also note that this inequality also holds for codimension too. a weaker version holds for any codimension, meaning what is a weaker version? Oh, in the weaker version, the constant on the left-hand side is not log Sn, but it is a weaker constant. So if we take f to be a constant in the previous theorem, we can recover the classical fact saying that among all closed n-dimensional minimal hypersurface of Sn, the unit sphere, the equator has the least volume. We want to point out that there are several ways to deduce this classical corollary. First one, we can use the new isoparametric inequality for minimal surfaces in Euclidean space, which was established very recently by Prandtl in 2021. Or we can use a monotonicity type argument or the heat kernel comparisons by Chang Li Yao for any codimension. And actually, there is a more general statement that also holds. That was proven by Brian White. It says that if you have n-dimensional submanifold in the Euclidean space, any codimension, so that the size of the mean curvature is at most 1, then the volume of that submanifold is at least the volume of the unit n sphere. Well, we look at the relation of our log Sobolev to Yau's conjecture. Well, assume that sigma is a closed minimal hypersurface of Sn plus 1. If we let gamma 1 be the first eigenvalue of the Laplacian operator on sigma, then if we look at a linear functional on Rn and we look at the restriction on the unit sphere, then the linear functional solve that the negative Laplacian of L is NL. So that N is an eigenvalue. And because of that, the first eigenvalue has to be less than or equals to N. We recall the fact that the first eigenvalue of the unit sphere of dimension N is N. Then it has been a conjecture by S.T. Yao that the first eigenvalue is actually N for any closed minimal hypersurface of Sn plus 1. In this direction, Choi and Wang in 1983 proved that the first eigenvalue of sigma has to be at least n over 2. And this inequality is actually strict. That was pointed out by Prandtl. So this inequality is strict. The relation between Yau's conjecture and log Sobolev is supported by the classical fact, saying that if there is constant alpha, which is greater than 0, so that the following log Sobolev inequality holds, then lambda 1, the first eigenvalue, has to be at least alpha. So we put our log Sobolev inequality here for comparison. So that in the future, if one can improve the term log Sn here to log sigma, then it would imply that the first eigenvalue has to be at least n squared over n plus 1. And this would be very interesting because asymptotically, n squared over n plus 1 is close to n, which is the constant expected by SDL. So we sketch of the proof. We can assume that sigma is connected, because if sigma is not connected, then we can apply this inequality on each component of sigma, then we sum over them. So for now, we assume that sigma is connected. Then after multiplying f by a positive constant, we can assume further that we have the relation. F log f integral of f log f is a constant depending on an n, like this. Integral over sigma of gradient f squared over f. Then with this scaling, we need to show that the volume of the n sphere is less than or equals to the integral over sigma of f. Well, by the scaling, there exists a solution to the equation, to the following equation: divergence f of gradient u equals to the left-hand side of the scaling minus the right-hand side of the scaling. Well, we note that sigma is a closed submanifold. Therefore, we don't have a boundary condition. So the scaling here is necessary and sufficient for the existence of the solution. So if we let G sigma denote the induced metric on sigma, nu is a unit normal vector field on sigma in Sn plus 1. And then we denote 2 nu. 2 nu is as the scalar second fundamental form in the direction of nu. Then we define the modified lower contact set by the following formula. So if we look at the proof of Caprese or the proof of the Sobolev type inequality for symmetric tensor that presented previously, then we don't have S and T here. So the S and T here introduced is like a cost. Is a cost for curvature. So yeah, it is a cost when you have absolutely no curvature, then you don't need S and T here. And similarly, gamma u in the set gamma u, we require that the Hessian of u minus S multiply second fundamental form plus Tg T times the matrix has to be non-negative. And the term S and T multiply these matrices here are the cost of the curvature. Then we define the map phi, which is defined like phi of xst is gradient of u plus s nu plus tx. Then similar to Caprese's proof and also inspired by Brando, we have that the unit ball of dimension n plus 2 is a subset of phi gamma u. Instead of just gradient of u gamma u, like in the proof Caprese, here we need to accommodate some curvature. So it is phi. So what is phi? So phi is a gradient of u plus s nu plus tx. Moreover, we can show that the Jacobian determinant of phi is controlled by the f and u and t here. And in gamma u, we also have a relation saying that f to the 1 over n plus 1 subtract square root of 1 minus gradient u square plus t is non-negative. So if we put these things together and apply the area formula, we would reduce the theorem. So we start with the identity. So say that pi unit ball times the volume of unit ball n plus 1 of dimension n plus 1 is the integral over the ball of dimension n plus 2 of this function. Then we make the change variable. Psi equals to phi of xst. And the next inequality is because of the second lemma. Second lemma here. So it says the determinant of the change variable maps is controlled by a term by that is by the term formed by f, u, and t. So this is the term that controls the determinant of the change variable map. And although this integral looks scary, it turns out it has very elegant form, which is pi over n plus 1 integral over sigma of f. And that finishes the proof of the inequality. So we may stop here. Thank you for your attention.
Thank you, Doanh, for the very nice talk. So we have time for questions and discussions for Doanh. Any questions, discussions? Let me ask first when we are waiting. So what's the current status of the Yau's conjecture? Like what you say, lambda 1 greater than n over 2 is the best bound for now?
Yeah. In a general case, that is the only progress. If you assume a much stronger condition saying that sigma, the hypersurface is isoparametric, then it is solved. So by being isoparametric, it means that so at every point, the second fundamental form has the same eigenvalues. So eigenvalues are the same at every point. So that is a very strong strong condition. And in that case, the conjecture was solved. In general case, n over 2 is the only bound.
And in your inequality, you said clearly that if you can replace the log of Sn by log of sigma, then you have a very nice bound, right? I mean, in principle, in principle, I mean, like, what would be the idea to do that?
Yeah, that is an excellent question. So I personally think that if you follow this ABP proof, then some significant idea has to be made, because why Sn? What is the difference between Sn and sigma? What is the role of Sn in the proof? Well, Sn is convenient because it is flat enough so that the normal bundle could cover the larger sphere very nicely. Right. But if you replace Sn by sigma, then the normal bundle may have some intersection. So in the area formula, you have to count the multiplicity. The times, how many times this normal bundle intersect. So that is where this ABP method failed for, I don't know, I mean, it may not fail, but I failed, I personally failed. I cannot prove that.
Thank you. That's great. Are there questions or comments to be made for Doanh? Go ahead, please.
Thank you, Doanh, for a very nice talk. How about the higher codimensional case of the logarithmic overlap inequalities?
Thank you for your question. Yeah. Yes, there is a weaker version of the higher codimension. However, yeah. So you see this term right here.
Right.
The term log Sn in higher codimension. There is another term that looks similar to this, but not quite. It is a weaker constant. And so it means that in a weaker version, we can establish this inequality. However, the inequality is strict. So the left-hand side is strictly less than the right-hand side. Again, the constant log Sn here is replaced by a weaker constant.
And so in the codimension bigger than 2, then do you expect to have a soft inequality, or are there any obstruction?
Well, I think there is I honestly don't know. But I expect the same inequality would hold. However, I'm not so sure that the ABP method can. I'm not sure. I'm just not sure because well, if you look at the work by Simon Prandtl in 2021, he proved an isoparametric inequality on minimal hypersurfaces, and that inequality is also sharp for codimension 1 and 2 only. In higher codimension, that inequality also is not optimal. And the constant in Prandtl's paper is the constant here is very similar to the constant here in our paper is very similar to the constant in Prandtl's paper. So there is some difficulties in higher codimension.
Thank you.
Are there other questions?
So can you come back to the proof of the inequality that you generalize the set result from convex domain to non-convex domain? Can you go back to that?
Yes.
Yeah, I found this very, very interesting, but somehow if you look at the statement of the theorem, that you see that A is positive symmetric is too strong, because somehow in this case, of course, in the proof you use the BDE that you need A to be coefficient, but just forget about the method of the proof and look at the statement, then somehow all you need is that determinant of A to be positive or something like that, right?
Yes, that would be yes, you are right. That would be.
So let's say that are there any way that to weaker the positive symmetric of the tensor A?
Yeah, if there is any way.
So right let's say that A belongs to the Gaussian cone gamma n minus 1. It means that maybe there's only one eigenvalue negative, but all the sigma k from from 1 to n minus 1 are positive. Right? I think that's the next step.
Yes. then I see what you mean. Actually, right now, if you replace like that, then I don't know, because in the proof it heavily relies on the fact that it relies on the existence of solution to the following equation.
Yeah, so that comes from the proof. The proof needs that condition, but let's say maybe there's another way to avoid its proof.
Yes, actually, there might be. I'm not so sure. And again, it is on in my head. I'm not. I have not written down explicitly. It is in my head. Okay. So in the sigma k version, one may look at, instead of A here, you can put TK,
Right.
Newton tensor, because the determinant of it is like a determinant of Tn. When A is uniformly positive, then determinant of A to the power 1 over n minus 1 is just determinant of Tn.
Right.
So if you replace by Tk, and there is a notion like a dual norm of of sigma k, like in the paper of Schrödinger. I forgot, Schrödinger and Kuhl or something. In the paper by Schrödinger and Kuhl, that was published in Indiana University Mathematics Journal. In that paper, Schrödinger and Kuhl introduced a dual norm to a sigma k norm, and if you put this together, then there might be a similar statement, but it's not like what you just said. So instead of looking at this system, you can look at the divergence of Tk, because if you assume that k belongs to the guiding cone, right, and Tk is positive symmetric, then you have divergence of Tk here. Then some similar statement could hold. However, it's not like the statement that you just said.
I see.
Okay. Thank you. So let me thanks Doanh here and stop the recording, and then we can have informal discussion now. Thank you, Doanh, again.
Thank you.